And then we're going to start chapter 5. In chapter 4, if you remember last time, we were not quite finished with section 4.5. And this is where we were learning about how to do integration using the method of substitution, or sometimes it's called U substitution. And one thing that was in common to all the problems that we worked on is that in every case, it was an indefinite integral, meaning that we were looking for a function, not a specific numerical value. So what happens when we use this approach, use substitution, when we're trying to find a definite interval, meaning we need a specific result? Well, there's one little change that has to be made to our approach. So this is the formal definition of what we're about to do. And the logic here is that if we're going to use U substitution, that's fine and it will work. But that means we have to change the limits of integration to correspond with the value of U rather than X. All right, so if you look at this carefully, you'll see we saw plenty of this in our last session. If this was an indefinite interval, you would not have any limits of integration. Instead, you would simply take or apply our rules of integration and you would end up with this result. But now all of a sudden, we're looking for a specific numerical value, which means we're calculating a definite interval as opposed to an indefinite integral. And so you notice by the way this is written, the limits of integration will be changed to adjust for the fact that now we're integrating with respect to U rather than X. Okay, so that's really the big change. So let's see how this works. Here's our example. So this one, if you notice, is a definite integral. So we'll need the fundamental theorem of calculus to solve for it, but we're also going to need to use U substitution. All right, let's take care of that part first. All right, so let's take a look at this and see if we can even use substitution in the first place. So let's just say we decide to let U be x squared plus 1. Then du dx would be 2x, and du would be 2x dx. So you notice there's a problem already. We don't have 2x dx, but we can supply the constant that's missing. So first, let's rewrite this. And you can see we're very close to having du, but not quite there. We need to supply that to ourselves, and we can do that very easily by multiplying and dividing by 2, as we've done in the past. Well, now we're looking pretty good. The only problem is, before we go any further, since this is a definite integral, we have to do something about the limits of integration. We can't just leave them there because those are meant for X. So since U equals x squared plus 1, when X equals 0, U would equal 1. That's going to become the new lower limit of integration. And when X equals 1, U equals 1 squared plus 1, which of course equals 2. And so now we can rewrite this whole thing as 1/2 the integral from 1 to 2. And now we can use our U substitution. We have U cubed du. See, that's the only change, by the way. That's it. That's the only, but it's easy to forget. You have to be very careful. It's easy to forget about this part. So using the power rule for integration, we have and then we can factor out that 4. And now using the fundamental theorem of calculus, we can evaluate this. We'll have 2 to the 4th minus 1 to the 4 inside the brackets. And so we'll have 16 minus 1 inside the brackets, and we ultimately end up with 15/8. And that's the final answer. All right. So I think they may have another example here that we can work on. No, we're going on to something else. All right. Now here they're going to talk about even and odd functions. Now, if you remember from pre-calc, how do you tell the difference between an even and an odd function? All right, let's go back and review that real fast. An even function means that no matter what x is, the function will have the same value for x and negative x. So as an example, x squared. So, and why is it even? Well, let's say that I evaluate f of 2, and then I evaluate f of negative 2. I'm going to get the same answer. And of course, that'll be true no matter what x I choose. So, for example, here, you can prove that this will be true for all x's in the following way. If you write the function is x squared, f of negative x, no matter what it is going to be negative x squared or x squared. And so this right here is our proof that this function is even. I mean, the one we did here with the 2, it's just a specific example. That doesn't prove that it holds for all cases, but this does. This is how we prove that no matter what x is, as long as it's in the domain of this function, f of x equals f of negative x, which means that this is an even function. And when you have an even function, by the way, in terms of the graphs, there's going to be symmetry from the left to the right. Okay, in other words, if you can see here, left and the right-hand side of the vertical axis are identical to each other. This is a characteristic of an even function. Also, only the functions where the leading term has an even exponent might be even functions. In other words, y equals x to the third power, for example, can't be even because the leading term has an odd exponent. What about odd? And what is odd? Well, instead of this, we have this. Instead of f of x, negative x, we have negative f of negative x. All right, let me just neaten that up a little. And so let me show you an example of this. All right, and that would be actually, let me just write it, just to be consistent, I'll write it as f of x. So if I try f of 2, and then negative 2, you notice how they're going to have opposite signs. It's the same number, but with opposite signs. So the f of 2 is 8, f of negative 2 is negative 8. And that means this is an odd function if it's true for all x's. So the way to prove that is to say, well, if f of x is x cubed, negative f of negative x will be negative x cubed, which is just get that out of there. Negative x which is x. So in other words, these are equal to each other. I'm sorry, this is cubed. That's better. Okay, so in other words, it's true for all x's, and so we conclude that y equals x cubed is an odd function. And here, the symmetry is with respect to the origin. In other words, the curve is the same on either side of the origin. All right, so I'll just mention that briefly here with odd functions. They are symmetric with respect to the origin, and even functions are symmetric with respect to the vertical axis. Okay, so now we remember what these are. Okay, now what they're going to do is show us that as far as integration goes. Oh, and by the way, I just want to mention too that not all functions are either even or odd. Many functions are neither. In fact, I would say the majority of them do not belong into either category. So there's no guarantee that any given function is either even or odd. Anyways, what does this have to do with integration? So the one on the left is an even function. You can tell just by looking at it. You don't even need to know what the function is. It's because of the symmetry with respect to the vertical axis. And then the odd function over here the symmetry is with respect to the origin, although unlike y equals x cubed, where the symmetry is between the first and the third quadrants. In this case, it's between the second and the fourth quadrants, but we still have symmetry with respect to the origin. So if we were to take the integral of this function, we're actually going to wind up with zero because the positive area and the negative area will exactly offset each other. That means we have to try something a little different. All right, so what we're going to do is this. Oh, and by the way, because of the symmetry, this area matches this area. Think of this as area 1 and area 2. We're guaranteed, because it's an even function, that area 1 equals area 2. Okay? These equal each other, but they're just different signs. Okay? So let's say, again, we'll call this area 1, and this will be area 2. Okay, so here's what they want us to do. In the case of the even function, and here it is right here. So between negative a and positive a, we can certainly integrate that directly and we'll be all set. But they want to make the point here, though, that you could also equivalently just take the area from, let's say, 0 to a right here, and then just double it. Okay, if that saves you time, you might want to think about it. And then for the odd functions, what we have to do, well, we recognize that that's just going to automatically go to 0 because of the symmetry. So if we do need to know the actual area, we would have to take the absolute values, okay, of f of x. But the actual area under the curve between those 2 points is 0 because this is positive, this is negative, and they exactly offset each other. All right, here's an example. They always manage to sneak in some trig functions on us. Now, this looks like a disaster. So Now they're trying, this is not something we've encountered so far. So they're going to let us determine first if it's odd or even. Okay. So now for this kind of thing, there are rules. Um, we can go find what we need. Believe it or not, there's a Wikipedia page that has every possible trig function you could possibly imagine. And I think I have it open right here, or I did. Oh, here it is. And it's just called, God, look how long it is. The actual title of this article is just simply trigonometric functions. So if you need to find this again, just type in Google, Wikipedia, trigonometric functions. It'll bring you right here. All these different relationships that you might not have even thought about are here somewhere. The only issue is finding what you need. It's so big. But if you scroll down the list, oh, there's all kinds of identities. You couldn't even begin to imagine how many identities there are. But some of these we use on a regular basis. Um, but there is a mention in here somewhere about signs. God, look at this. It's probably down at the bottom. Here it is. This is what I was hoping for. Okay. We have this notion of parity. And in fact, let me just copy this into our document so we don't lose it. And so they're also along the way mentioning to us that the cosine and the secant are even. And you can see why, because in this case, f of x equals f of negative x. The others are odd. And in every one of these cases, f of x is negative f of negative x. All right, so that being said, what they want us to do here is rewrite this. Well, first they want us to prove that it's odd. All right. F of negative x would be all right, so that means that the f of x is here. All right, and then we can use this table to our advantage. So the sine of negative x is negative the sine of x. So that's going to be, and then for the cosine, this is positive cosine x. And then again, with the sine of negative x, that brings us back to negative sine x. And then the cosine, same thing. So if you look carefully, you'll see that what you're seeing here could be obtained by simply multiplying the first expression, the original function, by -1. Or, which is the same thing as saying, um, oh, sorry, it's f of -x. That's right. So that means that it's an odd function. Okay, now how does that help us? Because we know that it's going to have symmetry about the vertical axis. Not the vertical, sorry, the origin. And so that means that we integrate it over those 2 points, the two sides will exactly offset each other, and we end up with 0. Okay, so, but now keep in mind the limits of integration are positive negative pi over 2. Otherwise, this wouldn't have happened. So, it's a kind of interesting example. So, yeah, because you notice how um, this is negative pi over 2. So everything from here equals the negative of what's going on here. So the total integral is 0. All right. Okay. So enough of that. So let's try a couple of these. The knowledge checks. This one looks really straightforward. Looks like we'll be able to solve for this one with U substitution, which is nice. All right. So why don't we try this? And oh, it's even nicer. It's easier because it's an indefinite integral. So we don't even have to change the limits of integration. Let's let U be t to the fifth plus 4. Du dt is 5t to the fourth. Du is 5t to the fourth dt. Now, again, it's one of those cases where we don't exactly have what we need. We're off by a constant. So let's supply that constant. Actually, let me rewrite it slightly. So I'm going to need to multiply and divide by 5 to get the du that I'm looking for. All right, and now we're in business because what we actually have here is 1 over 5 integral of u cubed du. Okay, so then we use the power rule on the u. And now, of course, since this is a indefinite integral, we need the c. And of course, u was defined as t to the fifth plus 4. And we're good. All right, let's see what choice that would be. T to the fifth plus 4 to the fourth power over 20. It's B. Okay, great. Oh, here we go. Now, with trig functions, we have to be extra careful now, because sometimes we can simplify these with the trig identities. But here it looks like they mean for us to use U substitution. So yeah, trig integrals can be extremely challenging since there potentially could be many ways of going about them. All right, so let's assume that they mean for us to use U substitution. Now keep in mind too, I'm going to go back and show you this small chart that I put together for the rules of differentiation. The derivative of the sine is the cosine. And the derivative of the cosine is the negative sine of x. Just keep that in mind while we're working on this. So let's just say we try u equals cosine x. Fine. Then du dx is negative sine x. Du is negative sine x dx. That means we don't have the negative that we need. We're going to have to supply it. All right, so we'll supply the missing negative, and this becomes all right. And now we can rewrite this as du over u cubed. Because remember, the u is cosine x. So of course we'll apply the power rule. These negatives cancel each other out. And of course, u was the cosine of x. Oh, actually, no, sorry. It's u to the minus 2. It's 1 over cosine squared of x. There we go. That would make it A. All right. So that's it for chapter 4. Now we can move on to something else. Now, up to this point, our focus has been almost exclusively on either trig functions or polynomials of some kind. Now we're going to go and explore very deeply two different types of functions that we'll need on a regular basis throughout all of Calc 1, Calc 2, any math courses you take. You might run into these functions. And specifically what we're referring to here is logarithmic, exponential, and other transcendental functions. Okay, so these will prove to be hugely important. So let's start here. So this is 5.1. And so we're going to start by introducing the natural log. Now you might remember from your travels that a logarithm is defined with a base. You might remember, for example, seeing something like this. Now, this statement says that 10 to the third power is 1,000. So the log to base 10 of 1,000 must be 3. Okay. So, or how about something like this? Okay. So what the log is basically doing is taking some constant and returning to the appropriate exponent based on whatever base has been chosen. So you also might have run across this, although possibly not. There's a special constant in math that we see all the time, and it's called E, very simply E. It's defined as approximately 2.71828. And if we take the log to that base, it's rewritten as ln of x, which stands for the natural log of x. So that's a very special case. It actually is so special that it gets its own abbreviation, natural log. The others, it's just log with some base. This is the only one where it just actually has its own name. So that shows you how important this is. The only other one that has a name is log to base 10. It's often known as the common log. Now, something like this you would have run into probably in a high school physics or chemistry class. It would have been used there for certain types of scales, like the Richter scale is based on log 10. Okay, but in calculus, it's the natural log you're most likely to run into. And in certain other applications like finance, it's a very common thing to run into E and log of X. So anyway, what they want us to do here is take a revisit of our general power rule. And, we know how this works, but it turns out there's an exception. We have kind of glossed over that up to this point. We know that, for example, the integral of x cubed is x to the fourth over 4 plus c. But it turns out that this rule only works as long as n is not equal to -1. Uh-oh, what do we do then? And you can see why, because if you did, you would end up with x to the 0 over 0. Well, we can't have division by 0. That's why the rule does not work for -1. So what do we do about it? Well, it turns out that, well, I'll give you a hint. They're going to keep us in suspense a little bit longer. It's actually equal to the natural log of absolute value of x plus c. Okay, so I've just opened up one of the mysterious doors for you. In that one case, we end up with the natural log of the absolute value of x instead of using the power rule. Now, this is the formal definition of the natural log. It's an integral. And I think they have a diagram of it somewhere here. It's only defined for strictly positive values, by the way. If you try to go to your calculator and type in a negative log, it'll just give you an error message. And also, 0 itself is not part of the domain of the log function. If you try to ask it for the natural log of 0, well, you're just going to get an error message. So for the function log x, the domain is all real numbers from 0 up to infinity, not including the 0. Now, what does this thing look like? Well, this is the integral that they're using. That shaded region is the actual value of the log. But if you were to go to, let's say, Symbol Lab and ask it to plot out the log of x, this is what it looks like. So it has a vertical asymptote at y equals 0. I'm sorry, x equals zero. And we notice, as I just showed you, if you try to take the log of zero, you'll just get an error message. That's because zero is not part of the domain. And you can see the function would be undefined at zero. And therefore, the vertical axis is an asymptote. So the function is really extremely negative until we reach one. Once we get past one, the function will start to grow relatively slowly. But anything between zero and one, the function will give us a negative number. Okay. So it grows really quickly until it hits this point. The intercept is one, where x equals one, y is zero. After that, you can see it increases at a pretty slow rate. It increases at a decreasing rate. Okay, so that's in a nutshell what the natural log function looks like. So what we're going to learn here is how to take integrals and derivatives for the natural log. So the domain, as we just mentioned, is 0 to infinity. The range is actually negative to positive infinity. It can reach every single possible value of y, not x, but y. So the range is all real numbers. Okay, it's continuous, it's increasing, and it's one-to-one. If you remember what that means, it means when x increases, the function always increases without any exceptions. And it's also concave down, okay, meaning that the second derivative is negative. Now, there's some key properties that we need to know, and you may have run into this before in another class. The natural log of one is zero, and that's actually true for any log, by the way. Um, Two, the log of a product is the sum of the individual logs. And again, this is true for any logs. Three, the log of a to the n is n log a. And finally, four, the log of a over b is the difference between the two logs. Now, these properties will come in very handy if we need to simplify a very messy expression so that we can integrate it more easily or do whatever else we have to do. So these properties can be awfully, awfully helpful. Like, for example, the log of 10 over 9 is the log of 10 minus the log of 9. Now here they've rewritten this as log 1/2 of 3x plus 2 because obviously the square root is the same thing as raising something to the 1/2 power. And then here they've got the log of 6x over 5. So you've got two terms that are being multiplied, log 6, log x, and one division. So you subtract log 5. So yes, so you have to be very comfortable with these properties because again, they will help you a lot when you run into some very messy expressions. Now this one is a mess. Oh my God, there's so much going on here. Let's take a closer look at it. Man, they really threw everything in that one. So first, you can break it up in stages, which is what they've done. If you notice, we've got a ratio. So we have, this goes in the numerator. This is the denominator. So we subtract, and then this one becomes, the exponent is 2 log x squared plus 3. On the right-hand side, what they're doing is, since that's a product, they're breaking it up into a sum of log x and then log x squared plus 1 to the 1/3 power. And then oh yeah, and then of course they're applying the negative sign to both of these terms. It looks like they're done here. That's about as simple as you're going to get. Still, what a mess that was, huh? Um, yeah, now here's some functions of the log. Log x squared looks like this because when x is squared, you can't have any negatives. So you're never going to run into, except for 0. 0 is still undefined here, but all the other real numbers are defined for log x squared. And of course, down here we have 2 log x, which means you're just simply making it a little steeper. E. Now there's that mysterious E. So they mention here that the log with base 10 is the common log. The natural log has a base of E. And E itself actually can be defined in a couple of equivalent ways. Um, Surprised I didn't mention it here. All right, I'll spill the beans. I'll show you the formal definition of E is it's a limit, okay? And maybe they're saving that for Calc 2. Okay. So that's where it's coming from. And it's got an interesting history. It's you might have heard of the mathematician Euler. He was a very famous mathematician, I think in the 1800s. I have to look it up. Hold on one second. You'll see this name all the time in math. Sometimes it's nice to take a step back and revisit the history of math and see where all this stuff comes from. This is one of the heavyweights in math history. Yeah, oh, I was even further back than that. Look at the 1700s. But a lot of things that we use on a daily basis in math were invented by him. But he didn't invent E, but he read about it in some papers written by other mathematicians. And apparently he was an egomaniac and he decided that we should call that number E. The E apparently stands for Euler. Okay. Now that's when you're an egomaniac, when you name a powerful new concept after yourself. He also invented the name for I. That was his idea. Oh, but that's just the tip of the iceberg. He was so famous. But anyway, so enough of that. So anyway, this is the natural log. By the way, the natural log of x and e raised to the x power are actually inverses of each other. If you were to plot them together on the same axes, you can see it pretty quickly. So all right, it's not perfect, but I hope you get the idea here. They are inverses of each other. And so here's log of x again. Anyway, this is what we were building up to. Some of the stuff you may have seen before in pre-calc, but right now this is the new part where we're actually taking the derivative of the natural log and e to the x. Now it turns out that these functions are surprisingly easy to take derivatives of and integrals. For example, the derivative of log of x is simply 1 over x. End of story. That's it. You'd think it would be a lot messier than that. And if you're using u substitution, of course, you would end up with 1 over u du dx. If you have something like this. Now, sometimes you will need the chain rule, though. If you've got the log of a function of x, then that changes it a little bit. But here we've got log of 2x. So u prime is 2. We divide by 2x, we end up with 1 over x. But down here, on the other hand, if you notice, it's not just 1 over x squared plus 1, because we do need the derivative of what's going on inside those parentheses. So when you take this derivative, you are applying the chain rule. And actually, you know what? Let me just mention something here. Actually, no, it's fine the way it is. But here, if you let u equal x squared plus 1, dx is 2x. And now keep in mind, in this book, u prime means the same thing as du dx. Sometimes they like to use that notation. The prime means it's a derivative. So that means that when you differentiate this, not u, it's log u. So that means in this case, the derivative is going to be 1 over x squared plus 1 times 2x. And that's what they have here. So the key of the whole thing is right here. When you're using use substitution like this, um, you will need the chain rule. You need it's 1 over u, but then you also need the derivative of u, whatever it happens to be. Oh, see now here they're throwing in the product rule. All right, let's see how that works. So let's just quickly review the product rule. If you have something like this, okay, so that means if you have x log x, f prime of x would be 1. G prime of x would be 1 over x. So we would have x times 1 over x plus log x times 1. Okay, so you get 1 plus log x. So that's where that's coming from. Now, ooh, look at this one. Now here they're relying on one of these rules that we saw earlier. This one right here. So in order to calculate the derivative of log x cubed, it's the equivalent of saying, let's try what you actually have here is equivalent of u cubed. Okay. I find the use substitution to be very, very helpful because it helps take your focus your attention on what you're trying to accomplish without all the messy details. I mean, um, once you realize that it's just u to the third power and u is a function of x, so you need the chain rule, then you just use the power rule for derivatives and you end up with that result. It's something called logarithmic differentiation. So this is actually based on implicit differentiation. And so here's what's going to happen. We've got this really messy expression, although there are many different ways we could solve for it. Logarithmic differentiation can often be used to make things a little bit quicker and easier. So first, let's copy this, and then we'll see what we can do to make it a little bit easier to work with. Now, of course, this is based on those properties we were just looking at a few minutes ago. Let me just quickly remind you what they would be. If you go back a bit, no, not the, well, yes, these are fine. You've got log of 1 is 0. The log of a to the n is n log a. The log of a product is equal to the sum of the logs, and the log of a ratio is equal to the difference of the logs. Okay, so that's kind of a hint as to where this is going. So what can we do with this expression to make our lives a little bit easier? We can try taking the log of both sides. Now, you're allowed to do this without changing the value of the equation. Anything you do on the left-hand side, if you match it by what you do on the right-hand side, it does not affect our results. So the first thing we're going to do is rewrite this as the natural log of y equals the natural log of x minus 2 squared over radical x squared plus 1. So what did that accomplish? All right, well, let's use the properties I just reminded you about. So in other words, since we had a ratio, a log of two functions, we can now turn that into a difference of the logs. And then because we have a couple of exponents here, I could rewrite it as well. Now, of course, the reason why I can do that with the second log square root x squared plus 1, of course, it's the same thing as the log of x squared plus 1 all raised to that power. So that's why I could do this. So now here we are. So what do we do next? Well, this is where the implicit differentiation comes in. It turns out that if you differentiate log y with respect to x, you're going to wind up with 1 over y times dy dx. Sometimes you see this written as 1 over y times y prime, or simply y prime over y. So we're going to take the derivative of both sides of this equation using implicit differentiation on the left-hand side, at least. On the right-hand side, we're explicitly taking the derivatives because we only have x's. So when you apply this, you'll have y prime over y equals. Now, for the first one, we have 2 log x minus 2. And of course, as we've seen before, the derivative log of x is simply 1 over x. Okay, so therefore, we can rewrite this as 2 over x minus 2. Now, the second term over here, minus 1/2 log x squared plus 1, that's going to be a little trickier because we're going to need u substitution. Let's take a look at this real fast. So what's happening here is this. Okay, so if you can think of, in this case, u is x squared plus 1, then du dx is 2x. Okay, so that means when I try to take the derivative here, I can factor out the negative 1/2. And what I'm going to wind up with is so the u prime or du dx is the 2x. In the denominator, I have the original u, which is x squared plus 1. Okay, now of course you can see the 2's will cancel each other out. And I ultimately end up with negative x over x squared plus 1. So combining these into our original expression, we're going to have, let's go back. Okay, here we go. So here's our original equation. And we know that on the left-hand side, we have y prime over y. Now, the first term we've already shown is 2 over x minus 2. The second term is x over x squared plus 1. By the way, I do want to point out that for this first term, um, 2 times log x minus 2, you don't need the chain, you don't need to use the u substitution because the derivative of x minus 2 is just 1 anyway. So we are using it behind the scenes, but since it's just x minus 2, we end up just 2 over x minus 2. But over here, the derivative of x squared plus 1 is 2x, so we need to take that into account. Anyway, so you might think we're done, but we're not. So because remember, what we're solving for is y prime or dy dx. So let's do this. And of course, y is the original equation, which is from way, way back at the beginning, right here. Or we could, actually, no, not that one, this one. Okay. So the y is equal to x minus 2 squared over the square root of x squared plus 1. And then you can multiply it out if you want to, but you can just leave it like this. So this is our final result. And keep in mind again that y prime is just one of the ways of expressing a derivative. Y prime equals to y dx, which also in turn can be written as f prime of x. It's all the same thing. So this is our ultimate answer. Now, of course, like I said, you could have approached this in a different way. When we started out, you could have, for example, maybe tried to simplify it a little bit, but most likely, whatever alternative approach you would have taken would have probably taken longer than this. Okay, so one of the motivations for using logarithmic differentiation is that it often can make things a little bit quicker. And that's not a bad reason for doing anything. Okay. So yeah, they went ahead, it looks like they did combine it. Um, but that wasn't absolutely necessary. So anyway, and then just in general, as we just saw, this derivative is u prime over u. Now, if the function is definitely positive, we don't really need the absolute value signs. But technically, we are taking the derivative of the log of absolute u because we know that it can't be negative. So here, for example, we've got log cosine x. So here we'll let u be the cosine of x. And once again, we'll consult our chart, the derivative of the cosine. Now, of course, it's possible that you've already got this memorized, but maybe not. Negative sine x. And so you basically have your derivative in the numerator. And in the denominator, you have u. Okay. And of course, if you remember, the tangent is simply the ratio of the sine of the cosine. So if you feel like you want to simplify it, you can write it as the tangent instead of the ratio of the sine of the cosine. So with trig functions, there's so many different identities you can lean on. Okay. All right. So knowledge check number one. Now here, all they really want you to do is use the properties of logs to rewrite it. We're not taking the derivative or anything like that. So let's do that. Okay. So let's see. Well, one thing we could do is rewrite this as, okay. And now since this is a difference of logs, we can rewrite this as, and that's realistically as simple as we're going to get it. So let's see what they're, no, there it is. It's D. All right. And then we have this one. Now, this is different. We are taking the derivative. All right. So the first thing we can do to make it a little bit simpler, um, although, it maybe in this case, it won't make any real difference if we split it up into three parts. Usually that might help with integration, but something like this, let's just use substitution and let's let this entire expression. And remember, this is sometimes written as U prime. So that means that um, the derivative here will be U prime, which is 16x minus 4, divided by the original U, which is 8x squared minus 4x plus 11. And as long as they can't be simplified, we're done. If you could simplify it, usually you try to, but it doesn't look like it here. All right, which one is that? That would be D. All right. So that was 5.1. So what's coming up in 5.2? Let's find out. Aha. So now we're going to see what integration is like using natural logs and exponentials like e to the x. Okay. So if we know how to do derivatives, we should be able to figure out how to do integrals. All right, here we go. So first, they're going to give us a rule for integration. If you have the integral of 1 over x dx, then the integral is the natural log of absolute x plus c. Now, this is an important one because this is what makes it possible to integrate functions of x as opposed to simply x 1 over x itself. Okay, so we have 1 over x dx. But we'll find that this one is very, very helpful. Okay, we can use a lot of use substitution on these types of cases and get answers very quickly. Okay, so for example, 2 over x dx. First, we factor out the 2. And then this piece by itself is just the natural log of absolute x plus c. Okay. Oh, and of course, if you want to, you can rewrite this as log x squared. You notice they dropped the absolute value signs because this clearly has to be positive. So of course they both mean the same thing. Remember, so that's based on that property we had earlier. That the log of let's say x to the n is n log x. Okay. All right, good. Now I lost. Here we go. Here we go. Okay. How about this one? 1 over 4x minus 1. So we're going to use u substitution. If we let u be the 4x minus 1, the u dx is 4. The u is 4 dx. Now, you can see we don't have the 4 dx, so we can supply that constant ourselves. And of course, oh, yes, so we can rewrite this as 1/4 d over u. And then we just have to substitute for the u. And that's something we haven't done in a while, which is long division of polynomials. So if you notice, in this case, the integral is of what we called an improper rational function. And the reason for that is because the degrees of the numerator and the denominator are equal to each other. So if you remember the way that works, in order for a rational function to be proper, it must be the case that the degree of the numerator is strictly less than the denominator. So here, the degree of the numerator is 2. And here it's 2, sorry. So what do we do about it? Well, that means we need to do some long division in order to reduce this to 2 simpler terms. All right, so let's try that. All right, so looks like the only factor that would work here is 1. And I'm going to put in 0x here to act as a placeholder because there's no x in x squared plus 1. Now I have to subtract. This becomes negative, negative, and negative. So in other words, we're already done. And what this is telling us is that this ratio is just slightly more than 1. So it's actually 1 plus x over x squared plus 1. Okay, so the long division, it made it possible to break this down into 2 simpler pieces. And so the first one is very simple. The second one is actually straightforward too, although we may have to make an adjustment to it. Let's take a look at this one first. Let's try u substitution. And of course, you can see we don't actually have the 2 that we need. So we're going to supply that because it's a constant. So we'll have, we'll rewrite this as 1/2 times 2x dx over x squared plus 1. And that means what we actually have here is 1/2 du over u. All right, well, we know what that means. That means what we actually have here is 1/2 log u plus c, and the u is x squared plus 1. And then this one is very simply x plus c. Now we don't need both c's. We'll combine them into a single constant. And then we'll be all set. All right, hold on. I have to clean this up a little bit. Okay, so when we're done, final result will look like this. So from the first term, we'll have x. The second term is 1/2 log x squared plus 1 plus c. So the tricky part there was recognizing that we're trying to take the integral of an improper rational function. And we ran into this before. And that's again because the degrees are equal to each other. We want the degree of the numerator to be smaller than the denominator. And if it's not, then we can take care of it with long division. And so that's how we wind up with the result. Perfect. All right. So they're throwing a lot of techniques at us here. And let's see. Now the next one. Ooh. Now this one's a little trickier. Um, let's see what they want us to do. Okay, so what happened here? So basically what we did here was we took this expression, this equation, and took the integral of both sides. Okay, so in other words, or we want to take the integral of both sides, but in order to do that, we have to rewrite it slightly. And now we can integrate both sides. And so even though we have dy on the left-hand side, the integral of dy is simply y. Now we can solve this the normal with whatever technique we might normally use. So in other words, it kind of threw us a curveball by writing it like this. It's just they've rearranged it so that the differentials are together on one side instead of in two separate sides of the equation. So when you see that, you can multiply both sides by the dx, then integrate both sides. And so the final result would be this. Now here is where we start to solve using our normal integration techniques. So what technique do they want us to use? Well, um, u, this is, well, first of all, it's u substitution. The question is, what should we use for u? If u equals log x, then du, x is 1 over x. Or in other words, du is dx over x. Okay, now if you look at this thing carefully, this ratio is du, and this is u. Okay, so that means we'll have, and it looks like a very strange result, but it is correct. It's like log x. Yes, that's right. You can have log x. Okay, so it's very strange looking, but there it is. Integrals of trig functions. Now you knew this was coming. Um, they love their trig functions. So now remember, we do have a chart that you can help yourself with. It's in Brightspace under the category tables, and let's go get it back. And you can see it does include some trig integrals, not all of them. There's quite a few more, but these are the ones you run into most commonly. So this could come in very handy when you're trying to solve for the integral of a trig function, like for example, the tangent of x. So let's look at our list and see if it's there. Ah, well, it's already there. But now that's interesting. I think somebody's mistaken. It says here this integral does not seem to fit any formulas in the basic list. Well, it's right there. I don't know what that's all about. Um, somebody goofed. So let's just use it. That's what the tables are for. I mean, you don't always have to use the most clever approach to calculating an integral. If it's on the table, just use it. Okay, so according to this rule that we see here, right here. All right, let me take a picture of that. So that implies, now that means that obviously we'll assume that u is x. So that indicates that du be dx. All right, that's all there is to it. They did go ahead and show you another way of doing it. Okay, even though it was there, it might be worth a while to look at how they approach it and see another way of going about this. So what they wanted us to do is this. Instead, let's just say we try to use the definition of tangent, and we said, that's great as far as it goes, but let's try it a different way. So we could use u substitution, but we have to be careful to choose the right u. Um, so let's say that u is cosine x. And if you remember from our previous examples from this table of derivatives. The derivative of the cosine is the negative sign. We don't quite have what we need, but we can supply that negative. So now what do we have is negative du over u. And of course, that means that we have negative log u plus c, and then we have negative log cosine x plus c. And of course, that's what we just got by looking it up in the table. Okay. So either way, we'll get the same answer. But it just seems strange that I mean, that table is in their book. So um, it is there if you need it. All right. But, it's good to know that there's other approaches we could take. If we have something that really isn't on the list, then we can try something like this. Ah, here we go. So they've reproduced some of these trig functions. Let's see if they're all in here in the basic list. Yeah, these are the same ones, but that's fun. Ah, now here what they're doing is they're giving us a case where we may need the Pythagorean identities. Okay. So now luckily I do also have a list of Pythagorean identities in that tables folder. So you can go look them up again if you've forgotten. So as soon as you see 1 plus, like tangent squared or secant squared or whatever, you might be looking at a Pythagorean identity. So here they are right here. So I'm just going to copy them all, and we can look and see if we have one of them in our integral. And yes, we do. You can see that this is the one we needed. Now we'll go look at our list and see if this is on our a table of integral formulas. The integral is secant x. There it is. No, wait a minute. It's not there. Oh, yes, there it is. It's right there. Okay, great. So I'll just copy this. Okay, let's try that again. Okay, great. So that means what we have here is the integral from 0 to pi over 4 of, actually, no, sorry, we don't need, we've already taken the integral. We have, now this is a definite integral, so we don't need the constant. Instead, we have to evaluate it over the interval from 0 to pi over 4. All right, so that gives us this. Okay, now of course, the secant is a little tricky to look it up. Your calculator doesn't have the secant button, but keep in mind the secant of x is simply 1 over the cosine of x. So if you look at the cosine of pi over 4, you'll get now it's 0.70. This is, it looks like it's radical 2 over 2. Hold on, let me just double check this. Yes, okay. So that indicates that the secant pi over 4 would be 2 over radical 2. But we normally rationalize ratios like this. We don't like to have square roots in the denominator because they're irrational numbers. So instead, we'll write it like this. All right, so we end up with 2 radical 2 over 2, which is radical 2. All right, so we have the log absolute radical 2. The tangent of pi over 4, we can look that up directly with the calculator, which is 1. Well, that worked out nicely. Now the secant of 0, look at it in the same way. We'll first calculate the cosine of 0, which is 1. So the inverse of that is just 1. And the tangent of 0 is 0. And so here's what we have. The log of 1 is just 0. So ultimately, the final answer would be right here. Okay? And we don't have the constant because this is a definite integral. Oh, and it looks like it went ahead and calculated the actual value. Right? So, yeah, the log of 1 is just 0. So, yeah, if you really need it, the log of 1 plus radical 2 is about 0.88. Okay. What else do they have for us here? There's so much going on. Knowledge check. Here we go. Um, so let's see what we can do with this one. All right, so why don't we try use substitution for this one? Okay, now we don't have the -8, so we can supply it ourselves. All right, well, that worked out rather well. So now we end up with -8 log u plus c. And of course, u is -4x squared, so we just make that substitution. All right, there we are. So it's negative 1/8. Yeah, it looks like it's A. Yep, that's A. Okay. And now what about this one? Ooh, this one looks kind of tricky. So I think we're going to wind up with another substitution. Let's try this. Equals log x du dx is 1 over x. U is um, dx over x. So that being the case, what we actually have here is u to the sixth. These two are the du. And so that and leads us to log x to the 7 over 7 plus c. All right, great. That would be B. All right. Now that was a tough section. That's a lot of techniques. There's a lot going on there. Learning about natural logs, e to the x, and then learning both about their derivatives and their integrals, and combining them with all the rules that we've been learning. So I would say that was a particularly challenging set of slides, to say the least. So what comes after this, by the way? Well, we had, let's see, this is 5.2. 5.3 is next, and that's going to be about here it comes. Inverse functions. Okay. So this is a pretty different topic. So we'll stop right here. Some of this we've seen in pre-calc, by the way, but we'll go back and review it. And the reason why they're bringing this up is because they're going to show us how to use this idea of inverses to find certain types of integrals can be solved this way. So that's what this is building up to. So anyway, so we'll definitely say that for next time, and I'll see you then.